And now I think we're ready to go. You ready to go?
Thank you. Everyone hear me okay? Okay, good. So hi, I'm Susan from AstraZeneca, for those who don't know. So today I'll be discussing some challenges we face when dealing with legacy systems and how RDKit might be able to help us. So to give an outline of this talk, I'll start with some background and motivation, and then go on to 2 studies which we performed using RDKit, and then finishing off with some conclusions and a note on future work. So the background, chemistry toolkits and legacy systems can be in place for many years, and replacing these can be often very challenging. I think AstraZeneca is no exception to this, and other pharmaceutical companies could possibly face the same challenges we do. So within the company, we use various softwares and chemistry toolkits. However, we are primarily BioVia-based. So in some instances, in some systems, we've created workarounds and built workarounds to handle edge and corner cases. So the question is, why would we consider anything else? So maybe the grass is greener on the other side. So going on to some motivations onto why we might want to change. So for example, we might have a cost benefit in changing our systems. So obviously RDKit is open source and so relatively cheap. So scalability as well. Maybe the new system is easier to put on the cloud. You don't need to mess around with licenses, for example. You get the benefits of open code based, obviously for RDKit, and you get other benefits as well, listed here and also not listed. So going on to reasons not to change, obviously you need to perform extensive evaluations. You need to understand how many molecules will be affected by your change. You also need to assess the implications on upstream and downstream processes, and accuracy also might be a reason to change and also a reason not to change. So based on how many molecules are affected and what kind of molecules are affected. Obviously, unknowns are very difficult to know, and people need to become familiar with the new system. So that's often a huge challenge. So recently we have begun to look at evaluating RDKit, and I'll highlight some of the findings in this talk. So what would happen if we replace our current systems with an RDKit-based one? So as I've mentioned, we'll go over 2 studies in this talk. So firstly, an import-export. So using RDKit, can it read and write AstraZeneca molecules without error? And then secondly, for those that can be written, are any features lost? And then the second study is looking at molecular uniqueness checking. So as Greg mentioned, in 2022, there was a release in RDKit for the registration hash. So we've been comparing it with what we currently use in our system. So just a note to say that this talk is not meant to be a moan about RDKit. We've through these studies, we've highlighted some problems with our own systems, and also how we store some of our molecules. We've also discussed some of our findings with Greg and also Chris from Schrödinger, so they are somewhat aware of what we've been doing and some of the findings that I've highlighted in this talk. So going on to the first study, which is import-export. As I've mentioned, we've done 2 things in this study. So firstly, can RDKit read in and read out AstraZeneca molecules without warning an error? So we've used our data set of around 6 million molecules, which are in the format of a mol file, and we've used RDKit functions mol from mol block and mol to mol block to read in and read out from RDKit. So here are the results from that. So most of the molecules were successfully written and read and written out, so over 99.9%, so RDKit performed extremely well. On to the next category. So for those that could be written out but had some kind of warning or error, these were less than 0.01%. So if we look at these, the majority of these were due to skipping unrecognized collection type, XMDL/selection. So these could have come from public collections, and really we're not really interested in this kind of data type. So we're not really fussed about this type of error and if we're losing this kind of data. The rest were due to conflicting stereochemistry warnings. So we looked at these kinds of molecules and we found about, we have this example here. On the left is the input, on the right is the output, and you can see the differences. You lose 2 wedge bonds, and that is okay because this is not a chiral center. So RDKit is performing what it should. So it's removing unnecessary wedges in this case. On to the last category, which are those molecules which could not be written out. So that was 0.05%. So the majority of these had the file format SCSR, which stands for self-contained sequence representation. So this is in an enhanced mol file format, which was made to represent biopolymers in a more condensed way in the mol file format. So RDKit cannot handle SCSR, and maybe that's something we should think about. The rest, so 15%, were due to explicit valence errors. So for example, we have this molecule here, which is dodgy. It contains a 5-valent carbon. So somehow these molecules were snuck into the database. And then there were less than 1% of other errors, which I haven't shown because they're the real minority. So looking at the next part of the import-export study, we asked the question, are any features lost? So we performed an exact match of the output mol block versus the input mol block. So here are the results from that. Again, RDKit performed very well. We found that 0.03% did not match by exact match. And again, we tried to categorize these into different categories. So one way of doing this is relaxing the settings on the exact match. And so we found that relaxing the stereo setting corrected 88%. So they were matched with a relaxed stereo setting, whereas the rest of them were matched with a relaxed tautomer setting. So if we look at those molecules in the relaxed stereo category, we found that RDKit sometimes removes and canonicalizes the wedges, which can cause issues. So I put minimal examples of such molecules on this slide. So this slide represents minimal examples of cases where canonicalizing the wedges can cause issues. In the first row, we have a molecule with a chiral center, which has a linear bond in the chiral center. And we find that if we switch around the wedge, it can cause the chirality to change. In the second row, we have a molecule that violates the triangle rule, which means that one of the atoms in the chiral center sits within the triangle formed within the 2 neighboring atoms. And again, if you switch the wedge around, you can find that the chirality changes. In the third example, we have a chiral center, which has 3 atoms that sit along the same line, i.e. the collinear. And again, if you switch the wedge around, you can find the chirality changes. So these can be issues that we should think about. On this slide, I've put minimal examples of cases where removing wedges can cause issues. So for the first example, it's okay. RDKit rightfully removes the wedges as this is not a chiral center. However, in the second case, we have a fused ring with nitrogen sitting at the ring junction, and it has a stereo bond. So we have 2 solid wedge bonds, which means that these rings are cis, and RDKit does not recognize that this nitrogen can have stereochemistry, and so removes it, and we lose this cis ring relationship. In this third example, there's a perspective drawing, and there is a dashed wedge that that means that the hydroxy points away from this amide bond, and RDKit does not understand this, so removes the dashed wedge bond, and we really lose that trans relationship. We also found cases where it can be also linked to problems with how we store molecules or represent them in our database. So, for example, on this first row, we have, again, a fused ring, and it has a data S group. So that's what this A label is, and it has the value 1 to 1. And this means that there is a 1 to 1 mixture of cis-trans fused rings. However, this is not recognized as meaning that, so RDKit removes it, and we lose that 1 to 1 meaning. So potentially we can think about storing these molecules in a different way. In the second row, we have a linear double bond. So possibly the chemist does not know the double bond geometry, and RDKit sanitizes it to an unknown double bond type. So maybe we can think of transforming these kinds of molecules to an unknown double bond type in our database. So going on to the second category of the exact match results, which are those which were matched when relaxing the tautomer setting, we actually found that these molecules weren't tautomers, but due to other reasons. So for example, the first row here, these two are resonance structures. So you can see in the output RDKit switches the double bonds around in the rings, and this is fine, it's an aromatic ring. However, the exact match does not recognize that these two molecules are the same. So this goes back to differences in aromaticity perception of different toolkits. In the second and third row, we have cases where RDKit sanitizes the mol file, so adds values to the mol block outputted. So in this row, there's a radical value being added to the mol block, and then in the third row, we have a valence value added. So maybe this is a problem, but we're not too concerned at the moment because we're more interested in organic molecules and less interested in inorganic molecules or reagent type molecules. So moving on to the second study we performed, which is about molecular uniqueness checking. So yeah, 2022, there was the release of the registration hash, and we've been looking to compare it to what we use it currently in our systems. So why do we need molecular uniqueness checking? So for example, we have a chemist here, chemist A wants to register a molecule into the database. It gets given an AstraZeneca ID. Later on, we have chemist B that wants to register a molecule which is actually a tautomer of this molecule. So the registration system should be able to identify that this molecule is the same and not give it a new AstraZeneca ID, but just a new batch number. Currently, in AstraZeneca, we generate what's called a compound key, which is a tautomer skeleton-like structure shown here. And we do an exact match of the compound key against the database of compound keys. And as an alternative, we can look to use the RDKit registration hash. So a bit about what the compound key and the registration hash looks like. As mentioned, the AstraZeneca compound key is a tautomer skeleton-like structure. And in our systems, we do an exact match. However, in this study, if we did a 6 million by 6 million exact match, it's quite computationally heavy. So what we actually did is we generated a NEMA key, which looks like this, of the compound key. And we use this as a surrogate versus the exact match we actually use in our systems. So a bit about the RDKit registration hash for those who aren't familiar with it. In generating the registration hash, you actually generate 7 different hash layers. So they all mean different things, shown in the first part of this table here. And RDKit gives you 3 presets of hashes to use. So for example, there's an all layer hash, there's a stereoinsensitive hash, and there's a tautomer insensitive hash. We've looked to use the tautomer insensitive hash as that's the most similar to what we use in our systems. Another thing about the RDKit hash is that you can also represent or look at what the tautomer skeleton looks like by getting the tautomer hash layer and pasting the first part of that into your sketcher. And so that's what I've done here to show an example. So ideally, if you have different tautomers, it should either generate the same compound key NEMA key or the same tautomer hash. In this example, I have 3 tautomers and it generates the same compound key, NEMA key, but actually it generates different RD-kit tautomer insensitive hashes, and I'll come back to this in a bit. So onto a bit about the methodology we used in this study. Again, we used the same data set of around 6 million molecules. We performed some standardizations to generate what I called the parent molecule. And on this parent molecule, we either generate the RD-kit tautomer insensitive hash or the RD-kit tautomer hash, or the compound key NEMA key. In doing this process, we have some failures, and here are some numbers that I won't read out to you. So to get out the differences, what we do is we merge on either the compound key or the tautomer hash, and then we unmerge and look at those with different merged mole IDs. So this is just to illustrate what I mean by merging and unmerging. I have the unmerged part of the unmerged data frame here. So on the left, we have 2 molecules and they have the same NEMA key, but different tautomer hashes. You can see that there are a greater number of merged mole IDs in the compound key NEMA column versus the tautomer hash column. And this means that the compound key recognizes these 2 molecules are the same, but RD-kit does not. On the right, we have the converse. Again, we have 2 molecules and they generate the same tautomer hash, but different NEMA keys. And you can see again, there's different number of molecules in the merged mole ID columns for both of them. And then in this case, RD-kit recognizes these 2 molecules as being the same, but the compound key does not. And I'll come back to this in a bit again. So a few numbers that might be interesting to you. So how many molecules are unique by each of the methods out of this 6 million? So as I've mentioned, we've used 2 different ways to calculate uniqueness. So both of them found just under 4 million unique molecules. And also we can look at the source of truth, which are the AstraZeneca IDs in the database. So again, that was just under 4 million, which is reassuring. So looking at the results of this study, how many differences were there in the 6 million? So 70,000 molecules had different merged mole IDs. But really, this might not be a good way to summarize the results, as some molecules might be present in many different groups. So really, you should do the statistic against the unique molecules. And again, you can calculate uniqueness in 2 different ways. If you use the compound key as the source of truth, then we found that 0.7% disagree. Again, we try to categorize the molecules into groups. And one way of doing this was clearing the cis-trans stereo before generating the NEMA key. And we actually found that this corrected the majority of the differences. So 91% according to the compound key NEMA key. Another thing we try to do is, instead of using the compound NEMA key, using the parent NEMA key, so not using the tautomer skeleton. And we found that corrected 4% of the results. And then we have another category. So looking at some of these molecules, the first category, which is the majority, clearing the cis-trans stereo before generating the NEMA key. I've tried to create a minimal example here to illustrate what I mean by this. So here we have an alkene, an E isomer of the alkene and a Z isomer of the alkene. And we find that RD-kit creates the same tautomer hash for these 2. And if we look at the tautomer skeleton of these, you can see that the alkene is included into the tautomer skeleton. And so RD-kit thinks that these 2 are the same. Whereas for the compound key, we find that the 2 molecules generate 2 different compound keys. So this basically highlights that the 2 different ways of generating tautomer skeletons. It seems that RD-kit only needs an atom to be involved in a conjugated system to be included into the tautomer skeleton. For the compound key, we are more strict in the fact that we actually need a push-pull system. So, for example, if we had a carbonyl here coming from one of the benzene rings, and a hydroxy coming from the other, then the double bond will be included into the tautomer skeleton. And for those two molecules, we would find that they would be the same by the compound key. So moving on to the next category, which is using the parent compound key instead of the, the parent instead of the compound key. So this should include differences by tautomer algorithm. So this is the case for the first two rows. We have a keto of a molecule and the enol form of the molecule, and we find that RDKit generates different tautomer hashes for both of them, whereas the compound key generates the same tautomer skeleton for both. So at the moment, RDKit cannot recognize keto enols in their registration in their tautomer insensitive hash. Also in this category, we found molecules that should not be there, so problems in the methodology. For example, explicit hydrogens, we maybe should have stripped them off before generating the compound key. So we have these two molecules on the bottom row, which differ from an explicit hydrogen in this one, and we find that it generates different compound keys, which should not be the case. I've also got the category which are unaccounted for, and I won't have time to go through these, but they're in the slides if you want. And so, yeah, I'll just go to the conclusions. So yes, in conclusion, we have started to assess the implications of using RDKit in our systems and also for molecular uniqueness checking. I've highlighted the results from two of our studies, so the results from import-export and the main sources of the exact match results. So for example, there's issues from canonifying and removing the wedges. And there's also differences in standardizations. There's also problems with our data as well. And I've also highlighted results from looking at the RDKit hash. So main sources of differences as well. RDKit does not differentiate between conjugated cis trans bonds. There's also some differences in tautomer identification, so keto enols, the requirement of a push-pull system for ours. And then there's a minority, which I haven't really covered, but you can look at in your own time. So in terms of future work, we look to try it out on some of our production systems. So thank you all for listening, and I would like to thank my colleagues also at AstraZeneca R&D IT, and also for Greg and Chris from Schrödinger for meeting with us and discussing some of our results. So yes, thank you.
So I think we're gonna have to pass the mic. I'll ask the question and you can answer it. There are some questions online. I'll start with one of those and then go to the room. So Preeti asked online why you're using the registration hash, or I guess the NEMA key, instead of using INCHI keys.
So INCHI at the moment cannot handle enhanced stereochemistry, I believe. The INCHI key cannot handle enhanced stereochemistry at the moment. There is an INCHI 2 coming out though.
It also has idiosyncratic tautomer rules that are different from the RDKit's other idiosyncratic tautomer rules. Are there other questions from the room? So some people in the room asked Discord questions as well, so maybe you can raise your hand too. So like Jimmy, you asked a question, but go ahead.
Do we need to repeat it for online?
For the people online, that is Charlie Hoyt's question in Discord, right?
Yeah.
But I haven't seen you in person, so I didn't like it.
So yeah, good question. I would say it depends on what system you're looking at changing. How and what kind of molecules you're interested in. If those edge and corner cases are molecules that aren't used in projects, and you're looking at molecules, you're really only interested in molecules that are currently interesting, then I mean it's okay to not deal with them for now. In the ideal scenario, you would deal with everything, but you only have so much resources. There are people within the organization whose job it is to be handed these molecules to do a quality, QA, and to manually check and assign them an ID. So maybe not a PhD student, or it's someone's job.
I think also just to follow up on that, some of them are also already kit fixes. So for example, some of the problems with the tautomer hash have been, I believe, fixed in the second version of the tautomer hash. And that a lot of how that happened was informed by the analysis that Susan did. And so some of it is things that we can do to just change the software in a straightforward way to fix what is a legitimate problem, like the problem with the cis-trans double bonds and the purely carbon systems. That's just was a problem in the original tautomer, or it's a design decision in the original tautomer hash that maybe isn't perfect for these cases, and so we revised that in the second version of the tautomer hash. Other questions from the room? Jimmy? Which cheminformatics system were you using before?
Yeah, as mentioned, within AstraZeneca, we use many different toolkits. However, we are primarily BioVia based. BioVia.
Former Accelera, former MDL. Sorry, I forgot Cynic, yes. BioVia, Cynic, Accelera, MDL. Whatever.
Sorry, can you repeat the question?
He said, I'll repeat it online. And he said that he thought that the system for 15 years ago was OEChem based, the registration system.
Yeah. I think there are many systems within AstraZeneca. It depends which one you're looking at. For our chemists and our projects, and I'm not going to say like names of applications, but we are using primarily BioVia.
Okay, so we should move on. One more. No, it's okay. Go for it.
So that is why we perform some standardizations before generating the hash and the NEMA key, compound key NEMA key.
Thanks, David, again.